Chatelier's principle. Next comes in Chatellier's principle. Chatellier's principle is for a reversible reaction, and in a reversible reaction, if there is a change that is brought about, right, the system will react such that it opposes the change that causes it. Meaning to say, let's say if I am increasing the concentration of the reactant side, the system will react and shift the equilibrium towards the product side so as to nullify the effect on the reactant side. So if a system in equilibrium, मैं simply बोल रहा था यार, मैं simply ये बात बोल रहा था कि अगर मैं reactant side पे एक change ला रहा हूं तो equilibrium occurs in a reversible reaction, right? तो equilibrium इस तरीके से react करेगा कि वो reactants को convert करना शुरू कर देगा ज्यादा से ज्यादा product side में, because आप reactant side पे change लाए हो, right? Because it has to nullify that effect. It wants to go back. The Chatelier principle simply states that if a system in equilibrium is altered by changing the dimension, then equilibrium will move in a direction that minimizes or nullifies this effect. For the case of concentration, let's say if I'm adding small amounts of acids, right, meaning to say I am increasing the concentration of the reactant side, the equilibrium favors in the forward direction, meaning towards the right hand side. After adding HCl was seen to be more on the orange. All I'm saying is, if I were to add a few drops of acids, a few drop of acid in the form of HCl into this equation, don't you think the concentration of the reactant side increased? And when the concentration of the reactant is increasing, it will start favoring the equilibrium towards the right hand side or in the forward direction. As a result, the yellow solution that you were initially seeing had now started converting into orange. चीज अगर मैं तुम्हें बोल दूं, let's say in this equation I'm saying that I am diluting the solution, meaning to say I'm adding water. Now that I'm adding water, meaning to say I'm increasing the product content, equilibrium starts favoring in the backward direction. So on dilution, the amount of water increases, so this favors the equilibrium towards the reactant side. Right. So as a matter of fact, if the concentration of the reactant is high, equilibrium moves towards the right hand side. Equilibrium moves towards the left hand side. And is, let's say I am adding NaOH. If NaOH is being added, an acid-base reaction occurs with this is the acid part, NaOH is an alkali. An acid-base reaction will occur, right? And as a result, this part gets consumed, right? The acid gets consumed. So basically, the concentration of your reactants is decreasing, and therefore equilibrium favors in the back. which an acid-base reaction occurs for equilibrium moves in the backward direction. Done. Let's say I have B2 plus and OH negative reacting to form B3 plus and half H2O. In order to increase the amount of B3 plus, we can use the following techniques. To increase the concentration of B2 plus, the amount of B3 plus could be removed, or you could add of the alkaline solution. Equilibrium moves towards the right. If there's a solid or a liquid in the equation, you will not consider it. Please understand that when the pressure is increased, equilibrium moves in a direction where the number of moles are less. Let's say for this equation, there are 2 moles on the product side and 4 moles on the reactant side. Forward direction.
Yes, sir.
For example, you have this equation: carbon solid H2O gas provides you with hydrogen gas and carbon monoxide gas. Please understand that on the reactant side, you have only 1 mole of gas, and on the product side, you have 2 moles of the gas. If you are increasing the pressure, equilibrium moves in the backward direction because there are less number of moles on the reactant side. Similarly, in this case, if you have H2 and I2 reacting to form 2HI, there are 2 moles on each side. If you increase the pressure, equilibrium does not move in any direction. Moving forward, effect of temperature has to depend upon the enthalpy change. If enthalpy change is endothermic, meaning to say it is positive, an increase in temperature will shift the equilibrium forward, and decrease moves it backward, and vice versa. If the enthalpy change is negative, meaning to say exothermic, an increase in temperature moves the equilibrium in the backward direction. The reason being, for an exothermic reaction, it is already giving out heat. According to Chatellier's principle, if you are increasing the temperature, it should nullify the effect. So if it's already giving out heat, it tends to move the equilibrium in the backward direction after an increase in temperature, so as to nullify or remove the. So in this example, if you see an endothermic reaction, enthalpy change is positive, forward reaction is endo, while backward is exo. On increasing the temperature, thermal decomposition takes place, meaning to say equilibrium favors the forward direction. Hence, dark brown solution will dominate or would be produced. And on decreasing the temperature, equilibrium favors towards the left hand side, and yellow gas is seen. For exothermic reaction, on increasing temperature, ammonia will decompose into nitrogen and hydrogen, which is why reaction moves in the backward direction. And on decreasing the temperature, equilibrium favors towards the right hand side. Haber's process is the manufacture of ammonia from nitrogen and hydrogen. Please understand that nitrogen is obtained through fractional distillation of liquid air, whereas hydrogen can be obtained from cracking of hydrocarbon or steam reforming. Right? Steam reforming is a process in which an alkane mixed with gaseous water provides you with carbon monoxide and hydrogen gas. One of the major products is carbon monoxide, which is poisonous, and this is the reason why it has limited usage. For Haber's process, you need to learn the condition: 450 degrees Celsius temperature, finely divided iron, 200 atm pressure, and the product formed is ammonia. Please understand that the yield of the product is 17 to 19%, and the equation revolves around like this, and the nature of the reaction is reversible and exothermic. Okay, so chemical kinetics will deal with the orientations of the reactions and what factors affect a reaction. Number one is catalyst. A catalyst from O levels, you know that it increases the rate of the reaction by lowering the energy of activation. A catalyst will never take part in a reaction. Please understand that. Catalyst will always provide an alternative route by that is the lowered energy of activation route. Catalyst will recover at the end of the reaction. Catalyst has no effect on the equilibrium yield. If it's a reversible reaction, it will decrease the energy of activation for the forward as well as the backward reaction. So basically it speeds up the process for both of them. For reversible reactions, catalyst increases the rate of the forward and backward reaction. Homogeneous catalysts are catalysts which will exist in the same physical state as your reactants. For example, I have gaseous reactants and let's say my catalyst is also gaseous, right? Let's say you are provided with this equation, NO2 reacted with SO2 to give you NO and SO3, right? Further, NO reacted with half O2 to give you NO2, sorry. Don't you think NO2 is being recovered back in the reaction? This is the reason why it is acting as a catalyst, and this is the example of a homogeneous catalyst because it will exist or it is existing in the same physical state as your reactant. Moving forward, let's say thiosulfate and iron reacted and gave you Fe3 plus SO4 2 minus, right? Fe3 plus further reacted with I minus to give you I2 and Fe2 plus, right? Please understand that Fe2 plus is not taking part in the reaction, it is being regenerated, and that is why it is acting as a catalyst. Heterogeneous catalysts, reactants and catalysts exist in different physical state. For example, we just did Haber's process. Your reactants were in gaseous state and your catalyst was iron, which was in solid state. Adsorption. Please understand there's a huge difference between adsorption and absorption, AB and AD. There is a difference between adsorption and there is a difference between absorption. If I said, let's say if I'm taking a glass of water and I'm throwing it on a wall, do you think that the water that was thrown on the wall surpassed it and was also seen at the back of the wall? Does that situation arrive? Or do you witness such a scenario? No, right? So basically the wall will adsorb the water. That is, adsorption is a surface phenomenon. Whereas absorption occurs throughout the material. So catalyst gets adsorbed on the active side of the catalyst. Adsorption process takes place via the active side of the catalyst. A catalyst will have its active side. You know from O levels that a catalyst will have its active site. Active site is the one that takes place, right? Let's say if this was a catalyst, this part tends to be its active site. Now, the material or the inhibitor will have to have this orientation, meaning to say only if it consumes the active side of the catalyst will it take, or will it perform its reaction? Only if it's consumed. This is, by the way, called the lock and key hypothesis.
सर फिर से समझा देंगे?
So for a catalyst to react, its active site must be consumed in the right way by the inhibited. This is the lock and key hypothesis. So absorption takes place via the active site of the catalyst. Active site is the vacant d orbital of a transition element. You knew from O levels that transition elements are specifically used as catalysts, right? Nitrogen plus hydrogen gave you ammonia, right? And an iron catalyst was used. This was a reversible process. Similarly, SO2 plus O2 gives you 2SO3. By the way, this is a contact process or contact reaction. This is the Haber's process, right? Beneath is the process called hydrogenation, that is the addition of hydrogen to an alkene. Autocatalyst is a reaction in which the product catalyzes the reaction. MnO4 plus 16H plus C2O4 gave you carbon dioxide plus H2O plus 2Mn2 plus. This was the Mn2 plus is an autocatalyst which starts off with this reaction. Initially, let's say the rate of the reaction is slow, then the product content increases, so reaction rate also increases. After completing the reaction rate, the reaction slows down. Initially, when you pour in reactants into a container, right, both of them will have their concentrations high, but as soon as they start to react, the concentration decreases, and hence this is a decreasing curve. As they start to react, the reaction rate increases, but when the reactants are being consumed, the reaction tends to slow down. Enzymes are biological catalysts. They are protein molecules and are very specific. So they catalyze only particular reactions. They will work through lock and key hypothesis. The lock is your enzyme. I told you that the substrate should be in the right orientation to consume the catalyst or the enzyme so that a reaction occurs. Enzymes will exhibit active site, which is a polar functional group. Polar as in it has a positive and a negative charge. So substrate combines with the active site of the enzyme. Hence, enzyme substrate complex is formed just like the one shown. This is your enzyme. E part is your enzyme. These are substrate molecules which come and sit onto the enzyme active site, and thereby they form a product amongst themselves. Next comes in Maxwell-Boltzmann curve.